Okay, let's start. So, okay. Next point, potential, electric potential. I'm not using the word energy. This is electric potential, what we call V. Okay, what is V? It's clearly related to some sort of potential energy, isn't it? The electric field, related to the electric field. Is there anyone that can give a precise definition or wants to attempt? I remember there was. Oh, hello. Anyone? Yeah. Potential for a charge to? Well, definitely, as any potential, as this is related to potential energy, definitely there will be an exchange from potential energy to kinetic energy. But I would like something more, bit more precise, maybe. So the accurate, let's say, definition is this one. So let us assume that I have 2 points, A and B, and there is some electric field. This is immersed in an electric field. Then we will define VAB, which is VA minus VB, the work done by the electric field to take the elementary charge Q from B, from, just a moment, I need to get this right, because otherwise, from B to A, divided by the elementary charge. So it is related to work done by the electric field, with a minus in front, because that's how we define potential energy. This is related to potential energy. Okay, it's always like that. You can go back to your first year book and look at gravitational energy, potential energy. It's exactly a similar definition. There is this minus involved, and is always related to work done. Okay, so let's try to be a bit more precise. Okay, so work done where? So how do I calculate, first of all, this? I could write it like that, isn't it? We know how to calculate the so I can choose a path from B to A. The work done is calculated by integrating the product between the electric field and the unit displacement. Well, here is the infinitesimal one. All of a path from B to A. Actually, because of the properties of the electric field, you could choose any path. Okay, the result would be the same. So this is really the definition. Just to put some values to it. So here, if I wanted to be even more precise, DL would be from B to A. Just to make the calculation, if you wanted to, let's take the very simple case where the electric field is let's take this situation, which is extremely simple. Over a length, let's say that the overall length is L. So L from B to A, we call it just L. So in this case, this integral is extremely simple. The only thing you need to be careful of is that these two vectors are in different directions. So the scalar product needs to take that into account. So actually, if you wanted to, you need to actually consider the component to do this property, the component of the electric field along this L that goes like that. So really, if I wanted to continue this chain of equalities, I would write minus 1 over Q time I forgot something. Nobody corrected me. What is missing here? Work is force times distance. The electric field is not force. It needs the charge involved. Okay, so that's correct now. And so we need here, we said now we don't need to do integrals because this is all very simple, uniform, but just to make the calculation. This is the component. Let me write it like that. With this thing, I mean the component of the electric field along the path with this direction. Okay, imagine this as an x-axis, for example, or a y-axis, and so on. So the component along that direction, and time the length. Let's call it L. Now this thing here, because of the fact the directions I've chosen, this is effectively minus the absolute value of E. There is a negative sign because they go in different directions. And so this becomes, the final result is Q goes away, the absolute value of the electric field time L. So what this formula is telling us is that there are several things we learn from this. Is first of all, we see that VA is bigger than VB. So in this situation, VA is bigger than VB. So always when there is an electric field somewhere, the point from where the electric field originates has a higher potential than the one down here, if you like. This point here where the arrow of the electric field points has a lower potential. That's what this formula is telling us. So VA, this may seem, okay, and so what? In circuits, this tells us it's easy to orient ourselves and to understand, in this point, for sure, there is a higher potential than there, because blah, 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 okay? So these things are important to keep in mind. And that's what actually all this, as I said, these first two lectures are about. I want to make sure we have good basis, although we are talking of stuff that is revision. Okay, is this clear? And actually, from this formula, we learn something else as well. That is this. Well, from the general formula, we learn that if you see, here we are defining the change in potential, in electric potential, through an integral of the electric field. So if we derive this integral definition, we end up saying that the electric field, sorry, the component now, I will use the same notation I used there, the component of the electric field taken along the path that goes from B to A is minus I've basically reversed this relation, and by deriving both parts as with respect to dl. The electric field is minus the derivative of the potential. Okay, so this is all very fundamental stuff that we will remember, try to remember. Oh, I'm losing pieces. Just need to check that the microphone does not get disconnected. Otherwise, you will be watching a movie of the 1900s. Okay, so let's move on. What do we mean by ideal voltage or current sources? Well, it's more about learning the symbol rather than what they are really. So for voltage sources, the symbol we generally use is this one here, and we will indicate, for example, with V1 the value of the voltage difference at the two ends. With the larger line, remember, is the part with a higher voltage and a higher electric potential. And there is also another symbol we may use, or the books may use. So this is an important point. Beware that different resources may use different formalism or notation. Okay, so try to deal with that. You know, it's unfortunately, it's what it is. We all have to deal with that. So that's why I'm telling you which are the possible symbols you may come across. This is for the ideal voltage source. And as any electronic component, because of what we've said previously, I forgot actually to stress this point previously when we said under these two assumptions that dq internal over the T is 0 and the flux linkage, the dphi over the T is 0, we, in this situation, simplify the things, and we don't need to use macro and so on and so forth. We can end up with the KCL, KVL, which we will analyze. This effectively means that that assumption effectively means that instead of using Maxwell equation, we will turn ourselves into using current and voltage. That's all. So that was the key of doing that assumption, that from now on, we will use only current and voltage. And so that's why it is important to define our sources here. So because from now on, we'll only use current and voltage, how do we represent a voltage source or a current source on a current voltage diagram? So if I plot, these are obviously called IV diagrams. We will see plenty of them. So a constant ideal voltage source is obviously represented by a line. What this means is that it can provide the same voltage for any current you ask it to provide. Doesn't seem very real, isn't it? That's why it's called ideal. Current sources, we indicate them with this symbol, say I1, or there is another symbol, maybe this one, and the corresponding IV is obviously this one here. Constant current, no matter what voltage you ask it to provide. Okay, and now we remind ourselves the Kirchhoff's laws, which we will indicate, for example, KVL, the voltage law. What does it mean? So this plays a role when we are dealing with a closed loop. Okay? So let us imagine that we are dealing with this closed loop. I will not add any components here, just for our definition. So let us imagine this is our closed loop. I can also indicate a rotation direction that I can choose. So the idea of the KVL is that if you sum all the voltage differences taken according to the rotation direction you've chosen, this should give you 0. Taken properly, carefully, and in the right order. What do I mean? For example, if I consider this direction of rotation, I mean, for example, that I will take VA minus VD plus VB minus VA plus VC minus VB. Okay? Always in the same order. So I will indicate as, according to the formalism we used previously, V, for example, VB minus VA, I will indicate it as VBA plus VCB plus VDC, VAD. Remember that this means, according to what I did previously in the definition of the voltage difference, this for me means VB minus VA, and correspondingly all this. This is one way of approaching KVL, so you go around, all around, and the sum has to give 0. Or another quite useful way of doing this, equivalent, completely equivalent, is to say, between these 2 points, you decide 2 points that may be meaningful to you. For example, A and D. You choose 2 paths, 2 different paths. They make a loop, obviously. So, for example, this path and this path. So the voltage across this path and the sum of the voltages across the other path must be equal. So that's the other point. So VAD across along a certain path, let's say path 1, has to be equal to VAD along another path, which here we could say corresponds to VA minus VD. I'm now explicitly breaking down what this means. Has to be equal to the first one, VB minus VA, plus VC minus VB, plus VD minus VC. Okay? So 2 ways of using the same idea. And the other important, obviously, law that derives from the fact that we are using the assumption we mentioned previously, and so we can define KVL and KCL. So KCL so in any node, we will define accurately, I mean, what is a node later on, but a node is any point in a circuit where 3 conductors converge, at least 3 conductors converge. So we can name the currents converging to this point in any way you like and defining whichever direction you like. So the idea is that the sum of all currents converging into the node must be equal to the sum of all the currents coming out of the node. So in this case, I would simply write there are only converging currents. I will write this one. Or the general one that I just said in words. The sum of all incoming, it must be equal to the sum of all outgoing. Okay, this is really in a nutshell, a very good summary, let's say, of these important, very fundamental laws that we will need. We will need a lot. Okay, so how do you feel? Okay, all this is something that I'm sure you were sure about. You know these things. Okay. Is this a bit clearer, at least, though, in your mind, now that we are doing this revision? Is it helpful? Okay. So, very briefly, fundamental passive components, which are obviously the resistor, the capacitor, and the inductor. So let's start with the resistor. The symbol, as you know, is this zigzag thing. Let's call this point A, this is point B. Let's take this direction for the current that is flowing to this. So with the symbol R, we indicate what we call the resistance of the resistor. Remember the difference. Resistor is the component, the physical component. The resistance is the electrical property that corresponds to that, that relates voltage and current. And the units, remember, is the ohm, which we indicate like that. And the fundamental law binding voltage and current for the resistor is, as you know, Ohm's law, which in this case we write like that. So VAB, be careful, I purposely put A and B to remember that this point is at higher potential than that, in this way that we've indicated there. So this means that if I was asking you what is VBA for the resistor, you will answer minus RI. Okay? So effectively, when we will be dealing with the resistors in a circuit, if the current is flowing in a direction that goes from the point, the starting point from which I want to calculate the voltage difference, then it will be positive, if you like, plus R times I. Otherwise, I need to take into account the fact that it needs a minus. Okay. Just for curiosity, remember there is another evolution, let's say, of Ohm's law that takes into account the physical property of materials, that says that, how the resistance is related to the geometry of a piece of material, and the physical property resistivity that is intrinsic of the material. So it kind of, we will not deal with this part. I'm just noting this passing, let's say. So still on Ohm's law. So at this point, what happens when we consider two resistors in series? We know that the total resistance is obviously the sum of the resistors. In parallel, this is equivalent to total resistance that is given by this formula. I'm sure you are very sure about these things. I'm not saying anything new. Just out of curiosity, if you have a parallel of 3, we indicate the parallel of 2. This is important to simplify notation when we do analysis. We will indicate it like this, with these 2 lines to indicate parallel. This means this R total is the parallel of these two resistors, okay? Just to simplify notation. So when I have just out of, again, just to see it once, the parallel of two resistors, if you work out this formula, will be, I will write it here, R1 times R2 over R1 plus R2. And there is an interesting note to do here, just so it is clear for everybody. When you have a series of two resistors, the one that R total will be dominated by the bigger of the two. That's obvious, isn't it? It's the sum. When we have the parallel of two resistors, the total resistance will be dominated by the one that is smaller. And this comes from here. Okay? That's something to keep in mind. When we have a parallel, the effective total resistance is near to the smaller of the two. When I have 3 now, well, R total now, well, I will indicate it as R1 parallel R2 parallel R3. Obviously, it follows this formula, simply with another term. And if you do the calculation, just because we may come across some of these terms later on in the next weeks, maybe next week, or maybe not this week. This may look like this. So it's always the product of all the terms divided by all possible combinations of 2. Right, just to see it once in your life. Okay, this is the resistor. Let's have a look. Oh, obviously, you can use the definition of linear and time invariant to demonstrate that obviously this system is linear LTI. We call it LTI systems, linear time invariant. Okay, so the resistor is LTI. So I think I can remove this. Okay, let's deal with the capacitor. We indicate the capacitor like that. Again, let's say this is VA and B. I will indicate some current flowing just to give to this piece of conductor some direction. Now, the capacitance C is measured in farad. And the relation between current and voltage will come in a moment, but before is the definition of capacitance, which is this one here. At any time t, Q at the plates, I'm sorry, let me do it this way. Because of electrostatic induction, the two charges at the plates will be exactly the same but opposite. And at any time, Q at time t over V, the potential VAB must be equal to C. Good. And so effectively from this definition, we obtain the integral form and the differential form that of the fundamental relations that relate to the capacitor. So the first one, we said integral and differential. So the integral is this one here. I've used T prime as the integration parameter. And the differential one is this one. You need to derive this integral form and you get the differential one, which is okay. Okay, some comments on this integral form. You can notice that it goes from minus infinity to t. So this immediately tells us that the capacitor is a component that reminds whatever has happened to him up until time t, from the past up until time t. So it's a system that has memory. Okay. Or sometimes you may see this written in the following way. Sorry. If for us time starts at t equals 0, and so whatever happened before is the past, this means that we need to take into account of of this by using what we call initial conditions, effectively. And so I can do this by writing this relation in this way. Plus VAB at time 0, a constant that takes into account, so this, effectively what I'm saying here, I'm splitting the integral in two parts, where this second term is effectively the result of this integral. It's past, and is summarized by a constant term, the initial condition of the capacitor. Okay. Remember that if you were to calculate the energy stored in a capacitor, we can demonstrate that this energy is given by this formula here. And, oh, I forgot to make a note still on this, a very important one. Now, this formula is telling us that the voltage at the terminals of the capacitor is the result of the integration of current. This means that while the current can be any wild function you can imagine, the integral of any wild function will be smooth, which we translate in the fact that the capacitor does not allow sudden changes of the voltage at its edges. So remember this, the capacitor does not allow sudden changes of voltage at its edges. This means, though, that it allows sudden changes of the current. We will demonstrate this in a moment, looking at the RC transients, probably something you've obviously done, but we will point out this thing. So this means that the capacitor is an element that is capable of giving bursts of current. It cannot give sudden changes in voltage, but it can give bursts in current. And this is used technologically. Do you know any use of this? For example, yes, very good example. Camera flashes, lasers, where high currents are needed suddenly, or a pulse generator, where you need high current suddenly. So capacitors are good for that. Let's see some more circuit-related properties. So the series of capacitors, let us remember that if I have this situation, this is equivalent to a total capacitance that follows the rule we saw previously for the parallel of resistors. So this opposite behavior, if you like. The series follows this rule. This can be easily demonstrated using the fundamental relation between charge and voltage. And the other one, I will remove this part. And the other one is the parallel connection of two capacitors is equivalent to the sum of the two capacitances. Okay, now we can demonstrate using the things we've said previously about linear time invariant that the capacitor is also an LTI system. So it's linear and time invariant. This can be quite, maybe sound weird, because I is C dv dt. It doesn't sound very linear, isn't it? But actually, is the, if you like, the operator, the system here is the operator derivative. And we know that the derivative is a linear operator, isn't it? So we can apply now what we've said previously about linear system and time invariance to this and demonstrate that it actually is. So try for yourself, and we discuss maybe next time if you have any problems. Try for yourself to demonstrate that this is a linear time invariant system using the definition we've said previously. Let's have a look at the inductor now, another fundamental component we will deal with. Oops. Okay, the inductor is indicated by this. Try to draw it better than me. That looks always like a resistor. So the inductor is the fundamental, L is the inductance and is measured in Henry. And the fundamental relation, as we saw previously for the capacitor, was C equal Q over V. In this case is the flux linkage, which is equal to L time I. So this the flux linkage at time t is equal to this. And from this equation, this fundamental relation, we derive the fundamental equation between V and I for the inductor that uses also one of the fundamental equations of electromagnetism, which is the Faraday-Lenz law. And so once you take also that into account, you end up saying that VAB for the inductor is L di dt, or the integral form. There is always, for these systems, the capacitor and the inductor, there's always an integral and a differential form. So the integral form is I 1 over L integral Okay, so again, as we did previously, we can write this one to explicitly emphasize the initial conditions, that this is a system that has memory, as we said previously. So this is the integral from 0 to t of V plus I at time 0. This is our initial condition. And so, as we did previously for the capacitor, we said the capacitor does not allow sudden changes of voltage. What can we say now for the inductor? It does not allow sudden in current, because what we are integrating now is the voltage. So the integral is always a smoother function. So it does not allow sudden changes in the current passing through it. Okay, this means, as we did now, let's say do that discussion again, this means that I can use the inductor to generate sudden spikes in voltage. Do you know anything where this is applied? Sudden spikes. Sorry? X-ray machines. I don't have a very in-depth knowledge of X-ray machines, but something more simple, everyday life, like in your motorbike or in your car, or it's a spark, the spark plug. The spark plug. You need some high voltage there to generate the spark. And there is an inductor in a circuit. If you suddenly break the circuit, the inductor will release a high voltage, and that makes the spark. Okay. Again, series and parallel. So if I take the series of two inductor, L total, this follows the resistor, so this L total is L1 plus L2, and I won't write the parallel, but you know, it's like the parallel of resistors. Okay, and as for the capacitor, the inductor is an LTI, a linear time invariant component. And so we can use our Kirchhoff laws, blah, 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 in all the circuits it appears. And it is a system that has memory, as we said. Okay, so we need to use, when there are circuits with the capacitor, with the inductor, we need to remember that. So at this point, time flies with you. Okay, at this point, I would like to briefly have a look at something that probably we will not deal with again. So in this, we said here we want to deal with analog systems. Now, when we deal with analog systems, we may have two types of behaviors we have to deal with. The first one is the steady state behavior, and the other one is the transient behavior of a system. In everything we do, we want to deal, for this course, with the steady state. Steady state means either in direct current regime, so using, you know, direct current power supplies and so on and so forth, or in alternate current regime, so using sinusoidal sources and blah, 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 blah. Okay. We don't want to deal with, in this course, with the transient response. It's another course by itself, okay? But here I want to give you a hint, which is basically, you know, the charging and discharging process of the capacitor in simple RC circuit. That is the transient response of an LTI system, which again, I stress it, we don't want to deal any further in this course. It's enough that, so we will briefly have a look at this response. And just to, because the reason we only look at this is that it's the only meaningful for the purpose of the course to have a look at, okay? But have in mind this important differentiation. So steady state means that I'm not looking at whatever happens for a short time and then disappears. Transient means that is something that holds for a short time and then dissipates, okay? So there is an entire section of electronics that is capable of dealing with that in a very efficient way. The way that I will show you here is very time-consuming because it goes through the fundamental equations of the components, okay? Solves differential equations and so on and so forth. So that's not the clever way of doing that, but we will do it just to remember it. Okay, so this is the only transient we will ever deal with. In all the other things we do, we assume that we are at steady state, so all transients have finished. Okay, so just to be more specific, when you have a circuit, for example, what does it mean that the transients have finished? When you have a circuit and you turn on the power supply, the system will try to adjust to produce a certain output given that specific input it has. So after 1,000,000 years, let's say, we are at steady regime And so we have the steady response of the system. But if you look at few microseconds, seconds, it depends, you have both the transient response and what would have been the steady response. So they are kind of mixed up. Okay, so that's what we need to separate here. So we will always assume from this point onward that any transient is over. Let's have a look now at this transient response just to remember ourselves. So let us assume that I have this circuit. And I want to find the voltage between these 2 points. So what I do is, if this is, let's say, the current I flowing into the circuit, I could write, using the fundamental equation for the capacitor, I could write that I, this is VC, so you look that I goes in the right direction according to the definition we've made previously. I'm taking VC as plus here, minus there, okay? So I can write, using the fundamental equations, that I is equal to C but also using KVL, I could say the voltage at this point must be equal to the voltage along this other path, isn't it? We've said it previously. So I could also write that V must also be equal to R time I plus VC. You see now that from this equation I can find VC and put it back there. So from here I will find VC, which is V minus RI. That I feed it back to this. Actually, I'll do something else. Sorry. I will find I from here. And so now I can say that this bit has to be equal to so I have a differential equation there, as you can obviously spot. Which I will just write like that. Tau, I call tau RC. So this is a linear differential equation, a non-homogeneous one. This is a constant term. So how do we solve this? The solution we can demonstrate is of this form. It's exponential plus a constant, because I need to solve also the non-homogeneous one. So as we don't have much time, the solution, if you put this back in, from imposing the equality, imposing basically using this equation here, so you put the solution in there, you can find that B is equal to V. But also, so this is one thing we find. Now, also we have to impose the initial condition. We haven't said that. So let us assume that initially VC at time 0 is 0, is not charged, the capacitor. So we use that in here to find that when t is 0, this is A plus B. So A plus B, this is the initial condition. I will write initial condition. A plus B must be equal to 0. So A must be equal to minus B, so minus V. And so finally we have what we wanted. VC is A is minus V, B is V, And so we have, I can write it in this nice form here, V times 1 minus E. And what this is showing us is that, and I will conclude there, is that V, if this is VC, and here I plot now the current, this is time, V goes like that. Is charging. The current, I can find it from here, and if you do the derivative of this quantity, you find that the current is actually V over R times E. So the current, actually, I will do it in red, looks like this. Our spike, the burst. The capacitor can give bursts in current, and that's there. So this is the example of a transient response that is the only one we will have a look at. And okay, with the inductor, you can do exactly something similar. Okay, similar analysis, and you will get exactly the same. So here, remember, tau was defined as RC. If you have an RL circuit, tau is L over R. Exactly doing something similar, okay? Okay. So we really are at the end. I was hoping actually to do a bit more today, but I'll probably have the time next time. There is something I wanted to tell you about, though. I like recording video lectures. So in general, I sometimes record, I have another module and I record the lectures. I pre-record the lectures and I give them to the students. So I was wondering, in case that there is anything that, you know, maybe I don't have the time to go through in here, but it's something that I really would like you to, that I explain to you properly. I will retain, let's say, the possibility of recording a video myself, because I generally do it in my office, and I post it for you, so that effectively you can, you know, look at it on your own. All right? Is that fine? Yeah. Okay. So if you can, next time, try to. We finished today at the transient response. So have a look at the material. So we finished there today. So next time I would like to finish chapter 1. So if you can, in the next week, have a look at the rest of chapter 1 on your own, using the references I have, that would be very useful, okay? See you next time. And I will post the videos tonight.